So let's look at a two-layered half space where there is a layer that is 600 millimeters in thickness. Let's call this layer 1. And then the second layer has an infinite thickness. And we have the modulus of the top layer is 500 megapascals, and the Poisson's ratio of the first layer is 0.35. And then the second layer, E2, modulus of 50 megapascals, and Poisson's ratio also of 0.35. And this layered system is loaded at the surface over a circular area. The intensity of the stress is 0.7 megapascals, and the loaded radius is 100 millimeters. Okay, so we have, this is the coordinate system origin, where the radial axis is measured from here, and this is the depth axis. So we have a point at the surface, let's call this point E, and this point is located at a radial distance of 800 millimeters from the center of the load, and we would like to know UZ at point E. And since this is a two-layer system, let's use the method of equivalent thickness. For this purpose, I'm generating E prime, a point just below point E at the interface between the two layers. And we know that the sought displacement of point E is really equal to the displacement at point E prime plus delta UZ, the compression of the top layer. So that is the compression between points E and E prime. So let's calculate the two. This is 1, and this is 2. Let's calculate the 2. So we start with the UZ at point E prime. In order to solve for UZ at point E prime, we look at a system that is a half space, really, that has an upper modulus and a lower modulus. Both of them are for with the E2 modulus, and this is where the point E prime is located. And let's calculate first this equivalent thickness. So H equivalent is going to be 0.9, that would be our correction factor, times H1, that's the original thickness of the top layer, which is 600 millimeters, and then times a cubic root of the moduli ratios, that is 500 divided by 50. And this ends up to be 1164 millimeters. So the equivalent thickness here is 1164 millimeters. The point E prime is located at capital R. This is the distance from the load center to this point, and capital R is 1412 millimeters. So this is simply 800 here, and here we have 1164. So we can use the solution from since this point is far enough away, it's the distance between this point and the loaded area is much larger than the radius of the load. We can consider this a point force and use a point force solution. So in the case of a Boussinesq half space loaded by a point force, the formula is the intensity of the force, 1 plus Poisson's ratio of the half space divided by 2 times pi times E times capital R. And then here we have 2 times 1 minus Poisson's ratio plus Z squared, the depth of the evaluation point, divided by capital R squared. So we can plug in the numbers. The point force is going to be pi times 100 millimeters squared times 0.7. This is Q. This is A squared. And everything here is the intensity of the load as if it was a point force. Then we have 1 plus Poisson's ratio. So that's 1 plus 0.35 divided by 2 times pi 50. That's E2 in our case. And Poisson's ratio 2. And then times 1412, which is the capital R. And then here we have 2 times 1 minus 0.35 and plus 1164 squared over, so that's the depth in the case of an equivalent system, 1164 divided by 1412 squared and close parentheses. If we make the calculation, we end up that UZ of E prime is 132.5 micrometers. Okay, the next step is to calculate UZ, delta UZ, E prime, which means the compression of the top layer, the change in distance between points E and E prime. So next step, calculating UZ, the compression of layer 1, use delta UZ E between E and E prime. So we have this problem, 0.7 megapascal loading intensity over a circular area with a radius of 100 millimeters. And in order to solve delta UZ E prime, we are looking at a half space with properties E1 and N1 and E1 and N1. So that's a half space. Thickness of the first layer is still 600 millimeters in this case, and we have point E and point E prime here. So this is a Boussinesq half space, and the sought entity is UZ E minus UZ E prime, and that means we take the displacements here, UZ E minus UZ E prime, and use that as delta UZ E prime. Since both points are far enough away from the circular load, they are larger than the distances are larger than 2 times A. In fact, the distance here is 800 millimeters, and the distance here is 800 squared plus 600 squared, and then square root of that, and that is 1000 millimeters. So both of them are much larger than A. So we can replace the circular load solution with the 0.4 solution, and what we need is this formula, P, the intensity of the force, times 1 plus Poisson's ratio of the half space. In our case, it's E1, so divided by 2 times pi times the Young's modulus. And then we have R, capital R, in parentheses, 2 times 1 minus Poisson's ratio plus Z squared divided by R squared. And for point E, we plug in the numbers. So that's P is pi times 100 squared times 0.7. 1 plus 0.35 divided by 2 times pi, E1 is 500. And then we have R, this is the distance to the point, 800 millimeters. Then 2 times 1 minus 0.35. And since we are evaluating a point at the surface where Z is 0, it's just, there's nothing here to add. And the calculation gives 15.4 micrometers. UZ at point E prime, that's going to be pi times 100 squared times 0.7, 1 plus 0.35 divided by 2 times pi times 500. This time we're using 1000, that's the capital R here. 2, 1 minus 0.35. And then here we have the depth squared divided by capital R squared. That's capital R squared. And that is 1000 squared, giving 15.7 micrometers. So this point and this point, they're really moving almost together. In fact, the layer here is not compressed because of the load, it a bit expands. You can see that the UZ E prime is a bit larger than UZE. That means that delta UZ E prime is equal to minus 0.3 micrometers. So the overall solution for the original problem, which is what was the displacement, vertical displacement at point E for the 2-layered case, and the method of equivalent thickness said it would be equal to the vertical displacement at E prime plus delta UZ E prime. So we plug in the numbers. From the first calculation, we got 132.5 micrometers, and from the second calculation, we have negative 0.3 micrometers. So the overall answer is 132.2 micrometers. What is interesting to note here is that the contribution of the second calculation was almost negligible, which means that in the original problem, the point E moved downward almost the same as point E prime, which was just below it at the interface between the 2 layers.